It is my great pleasure to welcome you to our second presentation for the competition of the Best Paper Award. And according to my clock, we still have 1 minute time. So I will just say hello to everybody who is on the call. The goal is to hear from the speakers for about 30 minutes, and then we will cut it off and open for questions. First, for questions from the reviewers, and then from questions from the general audience. And so I will not make any lengthy introductions. And with that, now my clock is exactly on the hour. So it's my pleasure to welcome Manish Shrivastava from the Pacific Northwest Lab in Richland, Washington State, who will talk about from stiff equations to deep learning, overcoming challenges in simulating complex aerosol chemistry. Manish, please go ahead. You can introduce your co-authors and use your time the way you would like to use it.
Thank you so much, and thanks for this opportunity to present this work. I am Manish Shrivastava. I am a senior earth scientist and at the Pacific Northwest National Laboratory, and my expertise is in atmospheric chemistry.
Manish, sorry to interrupt you. Just real quick, your camera seemed to be tipped down. Just if you can adjust your camera. Yep, great. Thanks.
Okay.
That won't be counted within your time limit.
Okay, thank you. Yes, so and also I am an active contributor to international research, review, and editorial activities. I also want to introduce my colleagues, Dr. Himanshu Sharma, who is a senior research scientist. His expertise is in physics-informed machine learning, deep learning, dynamical system modeling, and reinforcement learning. And Dr. Balwinder Singh, who is a senior computational scientist at PNNL, again with expertise in high-performance computing, software design, high-resolution Earth system modeling, machine learning, and artificial intelligence. So the work which I am presenting today has been co-authored by the three of us. And today's talk focuses on aerosols. So just quickly, aerosols are tiny liquid or solid particles which are suspended in the air all around us. And the reason they are important is there are like thousands and thousands of these tiny particles in the air. They scatter and absorb sunlight, so they affect the Earth's energy balance. They seed clouds because they act as nuclei on which water vapor condenses to form clouds. And in that sense, they affect precipitation, the water cycle. They also affect human health, air quality, and visibility. And just for perspective here, these primary particles are directly emitted. So they can be emitted from smokestacks, from vehicle emissions, whereas secondary particles are those which are not formed directly as particles. They begin their life cycle as gases. But the atmosphere all around us is a large chemical reactor with millions of reactions that convert these trace gases to aerosols. And I'm going to focus on secondary organic aerosols today for my talk. These particles can contribute more than 50% of the fine particulate matter budget, and they impact clouds and radiation. And for perspective, if this is the width of a human hair, a small PM2.5 particle is this red dot here, which is much, much smaller than even the width of the human hair. But there are thousands and thousands of these particles around us. The reason the secondary organic aerosols are so important and complex is because they are formed by chemistry that happens due to interactions between anthropogenic sources and biogenic sources. So for example, if you have a leaf, sometimes you smell a leaf and there is a pine smell coming out of it. Those are volatile organic compounds like monoterpenes. There is also isoprene. And these volatile organic compounds would normally stay as gases, but because of chemical reactions in the atmosphere in general, but also due to interactions with anthropogenic sources like sulfate, oxides of nitrogen, and other organic molecules, these interactions can make these gases convert to particles. And these particles are known as secondary organic aerosols. And you could, the figure here shows this blue smoky mountains. And this is an example of how tiny SOA particles or secondary organic aerosol particles, these are formed by chemical reactions of gaseous hydrocarbons released by the forest, and they scatter light. And you can see this blue smoke, the bluish tint here. And these are because of these thousands of secondary organic aerosol particles. And I would like to note here that predicting the transformation of organic gases to particles, this is one of the greatest challenges in aerosol cloud radiation interactions, weather and climate change, because even the IPCC assessments have recognized that these formation of secondary organic aerosols and predicting their prevalence in the atmosphere has been really difficult. Although primary particles can be easily incorporated in models, the secondary organic aerosol particles are represented by very simplified parameterizations because of their complexity. Just a quick introduction. When we look at atmospheric particles, they have a wide range of sizes and shapes. So these are transmission electron microscopy images of different types of particles which were taken at PNNL. And these are soot particles from the Amazon rainforest. These are from smokestack or vehicle emissions. So you see this fractal structure. These are biological particles from the Amazon fungi and pollen. And they have this structure. And the particles which I'm going to focus on today is isoprene-derived secondary organic aerosols. And the way if you look under the microscope, you see a core, which is made of sulfate and other, so sulfate and other inorganic components. But around them, there is a shell of secondary organic aerosols. So there is a core of, say, ammonium bisulfate and the shell of IPOX SOA. So the way we measure and characterize these particles, we use aircraft-based measurements in addition to other kind of measurements. This was a field campaign which was conducted over the Amazon rainforest. You see this huge rainforest here, and you see these interactions between NOx and other organic molecules. And as an aircraft flies, it can sample the plume and see this periodic rise and fall of secondary organic aerosols as it goes in and out of the plume. And these secondary organic aerosols, because they are formed by atmospheric chemistry, they are multidimensional systems. So there are more, and there are more than 1 million chemical species, and they vary across these different dimensions, the size. So there could be different particles with many different sizes, even in the submicron range. And depending upon their size, their chemical composition can vary widely. But also there are other properties which vary, like the volatility of these secondary organic aerosols, which governs their lifetime. The phase state, so they can range from liquid-like to semi-solid to solid, depending upon the temperature and relative humidity. So when it's warm and the relative humidity is high, they may be more in a liquid state. But when you look in the upper troposphere, these same particles can transition to a solid-like state. Their optical properties, their viscosity also changes. So because of this multidimensional system, there are fast and slow reaction timescales within these systems, and that can cause stiffness. And as we know, solving these stiff ordinary differential equations is challenging, but also representing them in computationally efficient manner is also challenging. So many of the global climate models use much simplified parameterizations, model approaches for aerosols, but advanced models represent these different particle properties in discrete size bins, as it is shown here. And because they need to carry different sizes, different tracers for different size bins, they quickly become computationally expensive. Accessing the response of climate to aerosols requires connecting molecular scales. So I have different molecules here, sulfuric acid, dimethylamines. So if we really want to understand the response of climate to aerosols, we need to connect the molecular scale processes to global scale processes. And so here, for example, a typical raindrop is shown here, and a small aerosol particle is shown by a very small drop. So you see there is a wide range of sizes and scales involved. We can measure some of these processes through field campaigns and both ground-based and aircraft-based. But for global climate, we really want to integrate all our process knowledge so that we can fill in spatial and temporal gaps of these processes. So the goal of this study is to enhance the predictive ability of Earth system models. And we aim to do that by demonstrating incorporation of complex aerosol chemistry processes efficiently in a computationally efficient manner, because these processes impact weather patterns, climate, and human health. And so there is a very important role of machine learning and data-driven processes to represent complex atmospheric chemistry, because many times these molecular scale processes could be so computationally efficient that they are not even represented in models. And so the role of machine learning becomes really important to incorporate these complex chemistry in a computationally efficient manner. And here again, the role of hybrid approaches could be really important. So for example, when we learn about processes from Earth observations, whether it's aircraft measurements or field measurements, molecular scale processes, their chemistry and physics, although they are computationally they could be computationally demanding, we can represent these processes through these neural network emulators. And then we can incorporate these neural network emulators within Earth system models and run these models online. So we can replace the more computationally costly parts of these complex chemistry with neural network emulators. And then we can run these models online. And we can also run them with high resolution. And this could help really represent the processes in these models which have not been possible to represent so far. This would often lead to recognizing uncertainties which we don't even know existed before. It could reduce systematic errors and cause more accurate climate predictions, and ultimately cause actionable climate science. So in this work, I'm going to focus on show an example of isoprene epoxydiol SOA. The reason we chose isoprene epoxydiol SOA is because isoprene is one of the largest global non-methane organic carbon emitted by vegetation globally. And it oxidizes in the gas phase to form IEPOX, but then this IEPOX gas is taken up by particles. So these particles need certain key ingredients like sulfate, acidity, and water content, so that this IEPOX gas can react on the surface of these particles through acid catalyzed nucleophilic addition and form IEPOX SOA, which is shown by these coatings. And that also I demonstrated through the transmission electron microscopy image initially. So this is just a schematic of all the reactions that can happen in the inorganic core. You have sulfate, bisulfate, water content, acidity, and this IEPOX gas which comes in can react on these particles. It forms IEPOX SOA. But as the phase state of these particles changes, when we cool them down, they become highly viscous. So as the shell of IEPOX SOA forms and its phase changes from liquid to semi-solid, it can cause a self-limiting effect in terms of reducing the further uptake of IEPOX gas. And there are different chemistry happening, gas to particle partitioning. There is particle phase polymerization reactions happening. There is also a combination of IEPOX with the sulfate here to form IEPOX organosulfates. So it's a pretty complex system. This is represented with an IEPOX with a aqueous chemistry module, which solves these stiff ODEs within a regional model. But our objective here is to emulate this complex chemistry in the aerosol phase with a neural network emulator and incorporate it within a high resolution regional model. And just quickly, we are using the WRF model, which is a regional weather forecasting model. This is widely used for hourly weather forecasting. It is a full physics model which solves which is used widely. And so what we are doing is we want to replace the component of aqueous chemistry of IEPOX SOA, which we incorporated in the model, with an emulator here. And then use our hybrid modeling approach and run the WRF-Chem model online with the emulator embedded in it. Here, I would just like to say that so far, the key innovations of our work is because we have overcome several changes. So far, running emulators embedded within chemical transport models to represent complex chemistry has had several limitations. and major challenges have prevented embedding these simulators in our system models. So one of them is preserving mass balance between gas and particle phase. So for example, when a given amount of high epox gas reacts and taken up by particles, we need to make sure that the mass which is taken from gas phase to particle phase is conserved. And also oftentimes, because it's so dependent on the particles, on sulfate and acidity, on plume conditions, the formation of hypox SOA could be highly skewed. And so emulating these greatly skewed input and output variables is additional challenge. And finally, previous attempts when they have tried to emulate even gas phase chemistry, they have had challenges because once a new emulator is trained, the errors quickly build up even within hours. So for example, the root mean square error between a default WRF-Chem model and WRF-Chem with a DNN embedded in it could build up very fast by several orders of magnitude. And that could impact our fidelity of the embedded model in predictions. So the way we overcame these challenges, those were our key algorithmic innovations in this study. And so we, in this case, this is a highly time-varying system. Basically, as you could see, there is sulfate in an urban location which evolves with time, but also it's a spatially varying system, and we embedded the deep neural network in the WRF model to replace its IPOX SOA chemistry module. We also ran several size sections here. So IPOX SOA has been represented by 20 size sections ranging from 1 nanometer to 10 microns. And this is a very complex aerosol sectional model. As I mentioned, many of the global climate models just have a few modes to represent this size-resolved chemical composition. And we are representing two different components of IPOX SOA, the IPOX organosulfates and IPOX 2-methyltetrals. And these are represented by the emulator. And we'll have several variables as inputs. These inputs are constrained by the WRF-Chem model. So this is just out of those 13 input variables I showed, this is just a schematic showing the 3D variables that we used from the WRF-Chem model as inputs to train our emulator. So this is water vapor concentrations over the Amazon rainforest. It's much more humid near the surface and much less water vapor in the upper troposphere. So you see there is a huge variation in the 3D space. Same for sulfate. Sulfate can be emitted in the formed in the plumes of the urban plume, but it can also be formed by cloud chemistry. So there is a huge variation in sulfate. And the IPOX gas, which is emitted by the vegetation that reacts in the atmosphere, but then it can also be carried by cloud convective transport. So there is 3-dimensional variations in different variables, and we use 13 of them, which includes both meteorological variables, but also chemistry variables, including temperature, relative humidity, sulfate, IPOX gas, and other things. So for training the deep neural network emulator, we used almost 2 terabytes of this 3D spatial and temporally varying data for training the DNN. But the ranges of the input data are physically constrained by the WRF-Chem model. As I mentioned, it's a full physics model. And so we are using actual predictions of the temperature, relative humidity, and other variables for training the DNN. And then with all these inputs of the model, which include things like water content, sulfate, ammonia, nitrate, and also the viscosity of these organic aerosols, which is allowed to vary in 3D, the coating thickness of IPOX SOA as it forms over the sulfate. So we have these 13 inputs, and we train the deep neural network. We used a hyperparameter optimization approach. And so in this case, we came up with 3 hidden layers and 64 neurons each. And there are 2 outputs which we are predicting, which is the fluxes of IPOX organosulfates and tetrals. And these are both components of IPOX SOA. So this is the 3D variation of IPOX SOA tetrals and organosulfates, which the DNN model is trying to emulate in 3D. And so coming back to how did we overcome some of the key mass balance challenges which have been very difficult to overcome. So instead of when we first tried to predict the concentrations of IPOX SOA with the emulator, we had limited success. And so what we did was we are now predicting the fluxes, and fluxes are caused by the aqueous chemistry module. So whatever IPOX gas is taken up by these particles due to these chemical reactions, is then applied to the particle phase to form epox SOA. So the fluxes are calculated from the aqueous module of the 3D WRF-Chem simulations. And that is what we are predicting. So we are emulating the rate of changes of epox between gas and particle phases. And once we emulate that, the fluxes are applied outside the emulator within the WRF-Chem model. And in that sense, it is preserving mass balance. So whatever reduction in gas phase epox is seen by this emulator, we apply it exactly equally to have an equivalent increase in the particle phase. And as I mentioned, because we are emulating the 3D phase space of WRF-Chem model, we came up with the model was predicting highly skewed, sparse, and skewed fluxes. And so this kind of skewed distribution is hard to emulate. And what we did was, before we fed it to the deep neural network, we did an inverse hyperbolic sine transform normalization with min-max to transform it into more continuous distributions. And these were then much easier to emulate with the deep neural network. The other thing which we did was, initially we were trying to use, because as we are running 20 particle size sections, so we have 13 variables times the 20 size sections, so 184 inputs. And then we had two chemical species which were output, and this 2 times the 20 size sections. So we were using a DNN which has all these 184 inputs and all 40 outputs. And this attempt failed. It did not perform very well. So instead of that, what we resorted is we took each bin, and for each size bin, we applied different deep neural network emulators. So we have 20 different deep neural network emulators for 20 size sections. And this greatly improved the performance. And what we also found is running 20 deep neural networks embedded in the WRF-Chem model did not increase the computational cost much at all compared to a single deep neural network which was embedded in the model. And so in that sense, this has huge implications, because now if we if we have an actual aqueous chemistry module, as it is looping through 20 size sections, or even when we increase the number of particle size sections, the cost will scale according to how many size sections we are using. But we can use as many DNNs embedded as we want without significant impact to the computational cost. So these are some of the results. Like these are predicted fluxes from the uncoupled DNN emulator. So we are still using the whole 3D domain of WRF-Chem to have a train validation split. And our target fluxes are aqueous chemistry epox SOA predictions, again predicted at the output of the aqueous chemistry module. And so this is the target here, and we have these predictions. And for example, I'm just showing a few different size bins from, say, 2 nanometers here to close to 1 micron. And as we can see, and I'm showing 2 different components, the epox organosulfate and tetrals. And the target and predicted distributions are fairly close. There is variation across different sizes, but the emulators are able to capture a lot of these variations here. And this is in the uncoupled DNN. But the actual test of this emulator happens when we now replace the aqueous chemistry module of epox SOA, embed the DNN in WRF-Chem, and then run the model. And if we plot these spatial variations, this is from the default WRF-Chem model, which has the aqueous chemistry module embedded in it. And then this is the DNN, which is embedded in WRF-Chem. So if we look at the default aqueous chemistry, the default WRF-Chem versus the WRF-Chem with DNN embedded in it, we see very similar spatial variations of predicted epox SOA. We also note that we only trained the deep neural network emulator with first 6 hours of WRF-Chem 3-dimensional data. And then once we trained the 20 DNNs, we just embed them and run it for several days, for more than a week. And we see that the root mean square error does not accumulate over multiple days, basically. And this was pretty encouraging. We also saw that the WRF-Chem DNN emulator is faster than the default WRF-Chem by at least a factor of 2. We did not profile the aqueous chemistry module, but we expect that the speed up of the aqueous chemistry module was much, much more than this factor of 2, which we are seeing for the whole WRF-Chem model. And also in the future, as I mentioned, if instead of 20 size sections, we have 40, 50, 60 size sections, we'll scale up. The default model will the computational cost may go down, but the DNN would be equally fast, much, much faster. I also mentioned that the processes which form IPOX SOA are very different in the surface compared to upper troposphere. So near the surface, IPOX gas can be reactively taken up by, there is liquid water content in the particles, so it can react with sulfate, water, and particle acidity and make IPOX SOA. But if we are looking at the upper troposphere where the temperature is minus 50 degrees Celsius, any water which is present in the aerosols is frozen. And so there is no aqueous chemistry that can happen. In addition, the shell which forms, the SOA shell which forms over this core, that is also solid. So this totally shuts off any aqueous chemistry. So in the upper troposphere, there is a very different mechanism which forms IPOX SOA, which is the transfer of 2-methyl-tetrol gases by cloud convection, and then its cooling and condensation of particles. And so it was also encouraging that our DNN model, which is embedded in WRF-Chem, could also simulate the IPOX SOA formation in the upper troposphere. And the same DNN could simulate these two different processes really well. Another test was it could also simulate the zeros like of IPOX SOA. This is also important. In addition to predicting the concentrations, it could also predict places where there was not much IPOX SOA formation. In addition, like we had trained and applied this DNN emulator to the dry season before, but now we said that, okay, let's test the robustness of this model and see if it can generalize to a completely different season, the wet season of Amazon rainforest, where we did not train the emulator. And again, here, this is a comparison of the default WRF-Chem model and the DNN, which is emulating IPOX SOA. And again, we see that the model does pretty reasonable job of predicting the regional variation in IPOX SOA concentrations. We see that the root mean square error with respect to the default WRF-Chem increases by a factor of 2 in the dry season. But we do note that accuracy can be improved by transfer learning to reduce the extrapolation errors to a completely different season. Still, this is pretty encouraging that the same emulator could generalize pretty well to a different season. So at this point, I would just like to reiterate some of my key conclusions. This is the first, to the best of our knowledge, this is the first successful application of a deep neural network which is embedded in a regional model, which actually simulates this very complex IPOX SOA multi-phase chemistry, because it depends on many factors related to the particle acidity, water content, the viscosity and other things which vary spatiotemporally. And also it applies it to 20 different particle size sections and looks at size resolved particle chemical composition as I show here. The mass balance is preserved with the DNN embedded in WRF-Chem. We did not see any error accumulation in IPOX SOA over multiple day simulations, even though we had only trained it with 6 hours of WRF-Chem data. It generalizes pretty well over a different season, showing the robustness in the model. We also note that while the default WRF-Chem, which actually runs the aqueous chemistry module, for it the computational cost will increase. It will scale with the number of size sections which are used. But for the hybrid model with 20 different DNNs embedded for each of the 20 size sections, we see no scaling, no increase with 20 DNNs compared to if we just ran one DNN in the model. So this is huge promise. The hybrid modeling could be a viable approach to represent processes which have been computationally prohibitive and completely neglected in our system models in future applications. And so with respect to future impact, I would like to note Earth system models lack this complex molecular chemistry processes because they mostly come up with simplified parameterizations. And so they could likely result in large and unrecognized uncertainties, because we don't even know, since these processes are not even present in these models, they are compensating errors in the models, and we don't even know what is the impact of these uncertainties in climate projections. Hybrid modeling approach accelerates the simulation across scales from molecular to submicron particle sizes, as I showed because we are using 20 size sections from 1 nanometer to 10 microns. This enables the inclusion of complex processes that were previously prohibitive. For example, now we can treat processes ranging from nucleation, when these clusters form and they start nucleating with each other and grow to CCN sizes. We can track that whole process with this hybrid modeling approach. So it has tremendous promise in including complex processes that were previously prohibitive for climate models. And this could support more informed policy and decision making in air quality, in weather forecasting, because again, I would like to note that very few models include the impacts of secondary organic aerosols and chemistry in weather forecasting and climate projections. And also it could inform public health. And it could, because it is so efficient, it could apply to more higher resolution models. As the global Earth system models are aiming towards higher and higher resolution, the cost of these aqueous complex processes might increase, but having these DNN emulators to represent these complex processes could actually enable us to do this efficiently. And with this, I would like to thank you for your time and want to acknowledge the US DOE Department of Energy Office of Science BER Early Career Award and Atmospheric System Research for funding. Thank you.
Thank you, Manish. And I will just use a quick personal note. Congratulations on winning one of those prestigious early career awards. That's wonderful. So, and I think you've shown us what you've done with your early career award. So I'd like to open it up for questions first to our reviewers. And I'd like to ask you, if you want to ask a question, to use the raise the hand feature. While I'm waiting here for some hands to go up, then I'll ask my own first question. So you said the chemistry, atmospheric chemistry is computationally demanding. So could you quantify this a bit more and say in terms of how much is in chemistry more demanding, or in computation, how much time, or in terms of fluent conversions, how much does it take compared to the other grid computations per grid block? What does demanding actually mean? If you do full chemistry, does it take 10 times the time it takes to update the grid block, or does it take 100 times, or is it? What is the actual cost, sort of?
Yeah, so I would say that it really depends on the chemical processes which are incorporated in the model. And actually, like, because these are molecular scale processes, the models which even implement this atmospheric chemistry, even in regional models, there are several simplifications which are used. So for example, like for 20 size sections, if I am running a detailed chemistry module in WRF-Chem, I have to advect 1,000 tracers, which include both gas phase and particle phase chemical components times the 20 size sections, and then times another 20 for each chemical component to represent cloud-borne aerosols. And so it really slows it down. So I would say more than 10x to 100x. And that's just with what we have right now. So compared to a simple model, which does not include this complex chemistry or does not include several size sections, you could easily, like with 1,000 tracers, if we are running at say 250 clusters here, 250 computational nodes, it is like 1 hour for 1 day of simulation, and that's just a small regional domain. And so if we scale it to larger and larger domains and higher resolution, and also include more processes, it will scale up much more than 10x to 100x.
Good. And so the factor of 2 improvement that you saw is just for the chemistry calculation, or for the code for the WRF code in its entirety?
It was for the whole WRF-Chem code. So we did not. Okay. Our thought is that if we had profiled just the aqueous, so we only replaced one component of chemistry. So as I mentioned, the SOA formation is pretty complex. It has many different chemical routes. So we took one chemical route, the aqueous chemistry module of it, And we have demonstrated that the whole WRF-Chem model sped up by a factor of 2. So if we did not profile that actual aqueous chemistry module, how much it sped up, but our expectation is that it must have sped up much more, because this is what we are reporting as factor of 2 was for the whole WRF-Chem model itself. And that was just for one chemistry process. So now if we were to do it for other processes, then we would expect much, much more speed up, and also the ability to include more and more detailed processes, which have not been possible so far. So we have demonstrated it for this case. And so because of this tremendous promise it holds, we think that it could be, this kind of approach could be used for more complex chemistry and other processes as well in the model.
Thank you. So I'd like to ask Yusuf to ask his question. Go ahead, Yusuf.
Thank you, Manish. Very nice presentation and paper as well. I have a question on the training data set. So you mentioned that the DNN was trained essentially on the 7 hours of 10-kilometer WRF-Chem output.
Yes.
I understand you selected that training data set because it's very well constrained using the aircraft measurements from the campaign, the NASA campaign and the Amazons. But have you considered maybe running WRF-Chem in a large eddy simulation, so sub-kilometer scale, given that you already have the aircraft measurements? Why wouldn't you consider going down to maybe sub-kilometer LES scale simulations to do that training?
Yeah, that's a great question, and I am sorry if there was a confusion here. So I was just showing the aircraft measurements as a motivation and introduction about how we build these processes in WRF-Chem model. We actually did not use the aircraft data to train the model. So what we developed these processes of high-epox SOA chemistry based on laboratory and field measurements, and we have tested the default WRF-Chem model with aircraft data in the actual field measurements to make sure that the default high-epox SOA chemistry processes are validated by aircraft measurements over the Amazon rainforest. This was a DOE G1 aircraft during the 2014 Go Amazon field campaign. So after we validated that the default WRF-Chem model, the processes which are in the model for high-epox SOA are, it can reasonably simulate the high-epox SOA which was observed by the aircraft, both near the surface and in the upper troposphere. So for the upper troposphere, we had another aircraft, which was the German Halo aircraft. And so that's how we could discover new processes that the formation of high-epox SOA routes in the upper troposphere are very different compared to near surface. So we actually discovered new processes in the model and we implemented them. But when we went to train the DNN, we actually used just the WRF-Chem data from the 6 hours. We used 3D spatial and temporal variations of these different chemistry and meteorology variables and their impacts on predicted high-epox SOA, which was actually predicted by the default WRF-Chem. So the aircraft was just used to validate the default model and to make sure that we have the right processes in the model. But the training of DNN just used the 3D WRF-Chem default model data itself. It did not use the aircraft data. But coming back to your other question, because these processes are already validated with laboratory measurements and with aircraft measurements, we think that even if we use an LES scale model to these process level chemistry relationships between sulfate, acidity, water content, other meteorology variables, these relationships will not change because these are given by both laboratory and field measurements themselves. Does that answer your question?
No, understood. I was just concerned about the mixing. So the turbulence scale mixing would not be resolved at the 10-kilometer scale. And that's one of the most important processes when we look at new particle formation, for example.
Yes, exactly. Yeah, I am totally with you on that. And because we are running the model embedded within WRF-Chem, we only resolve turbulence down. I mean, it's parameterized, right? So it's whatever the WRF-Chem model is predicting for turbulence interactions. But we could also embed this DNN in an LES scale framework. And then it would be able to capture the turbulence impacts because we only replaced the aqueous chemistry part of WRF-Chem and the turbulence was modeled, turbulence parameterizations and mixing was modeled by WRF-Chem itself. And so if we were to embed these DNNs in an LES scale model, that would be able to capture the impacts of turbulence and the fine scale heterogeneities, as you pointed out. But in this case, we were focusing on the differences between near surface and the upper troposphere. And because the processes are very different near surface compared to upper troposphere, as was validated by aircraft measurements, we could reproduce those with the DNN. But certainly this is something for future work, and this DNN can be embedded in an LES model in the same way as it was embedded in WRF-Chem to make these predictions.
Thanks, Manish. The reason I ask is it's really transformational work. So getting the training data more physically constrained would be the next big thing, I guess, for this type of work. So thanks.
Thank you.
Any other questions from the reviewers or from the audience in general? If I don't see any hands, so then I'd like to ask one or maybe two more questions that I have. One question I have is, in this work, have you seen any new insights into the chemical processes or into how chemical processes change for weather pattern based on your work? So it was for any new atmospheric chemistry that you also discovered or insights you had how the chemistry changes the weather. Anything interesting new that you observed?
Yes, so this is a great question. And my response to that is mainly because we only ran it for maybe a week or 2 weeks, right? In this case, our objective was to demonstrate that we can,
So you can reproduce, but I was just wondering if you used it as a scientific discovery tool.
Could you please repeat? Sorry.
I was wondering to ask the question differently. Did you use your new code as a scientific discovery tool to come to some new understanding of climate processes or weather processes? If not, that's fine. That would be.
Yeah, so
I know that was not part of the plan.
Yeah, it was not part of the original plan, but now, I mean, because we can represent these complex processes that efficiently, I think this would be the next step, that we could use it to represent the processes which we have not been able to represent in the model. But I would say this thing that it is widely recognized. I mean, it could be a very important scientific discovery tool because secondary organic aerosols, they are responsible for then 50 to 60% of the CCN, which happens in the atmosphere. And in places like the Amazon rainforest, where it's impacting the water cycle, the clouds and precipitation. And depending upon the size of these particles, we have also found in other related work is that if we have ultrafine particles, they can actually increase the transition of shallow clouds to deep clouds and cause heavier precipitation. And so depending upon the particle size, the chemical composition and hygroscopicity of these particles, they could have many very different impacts on things like transition of shallow to deep clouds that could impact local weather, local precipitation cycles, and their impacts could be seen downstream further. So getting the size result, chemical composition, and hygroscopicity is really important of these particles. And many times models, could just, they prescribe some sort of size distribution and hygroscopicity, or they don't resolve the full history of evolution of molecular scale processes to CCN sizes. And that could have big impacts on our understanding, on our predictions and projections. So that is, building these blocks of molecular scale processes where you can actually predict now the evolution to CCN sizes and their impacts on weather and precipitation, and is a really important step because now we can represent these processes which have been computationally prohibitive before, and then we can do more process discovery.
I have a
may
question.
I ask a quick follow-up question, Yusuf? This is because we were talking about the particle sizes. You showed these intriguing images of transmission electron microscope images of the particles in different sizes. And so how do different particle sizes and also the structure and shape of the particles impact the chemical processes? Is that something that's in the model, or is that just sort of an illustration of where you might want to go?
Yeah, that's a great question. So far we don't consider the shape. I mean, most of the particles are assumed spherical in most models. So we don't consider these fractal shapes or these very irregular dimensions. We do, we have taken the next step of complexity, where instead of treating the particle as homogeneously well mixed, we treat each particle size as a core shell particle, where the core is an inorganic core of sulfate and acidity, and then the SOA forms on the shell, which has been observed in the laboratory, and it can still interact with this core. It does have tremendous implications for further growth and development of these particles, because you can see if the shell of SOA on the particle, if it's highly viscous and it's subjected to smaller temperatures, then, colder temperatures, then it becomes more and more solid, from liquid-like to solid state. And then the solid will retard the further uptake of these particles and their growth. This also impacts their lifetime, because if it's liquid-like, it is able to partition with gas particle partitioning dynamically. And so if a particle which is liquid-like of SOA is taken over the oceans in places where there is not, it's highly dilute, the model could predict that the gases SOA can easily start evaporating. But now if it is a solid-like shell, if there is chemistry which has converted the shell from a semi-volatile liquid matrix to a semi-solid matrix, then it preserves its lifetime. So longer lifetimes, longer transport, and it could have much longer implications for as these particles are transported downwind. So even with the spherical size resolved chemical, and then also obviously depending upon the particle size, the diffusion of gases and the reaction in the particles is very different. And that's why it's really important to consider the size resolved chemical composition, because it impacts the histories of how the particle evolves to CCN sizes and what are its lifetime in the atmosphere.
Okay, so I'd like to give it back to Yusuf, who had another question.
Yes, this is Alex here. May I ask a question, please?
Sure.
Yes, very nice presentation. Congratulations, very interesting. You said that before it was computationally prohibitive to do this work which you have done, but what did actually people do to deal with it before the advent of neural networks and things like that?
Yeah, so I would like to note that many of the complexity in SOA formation processes are not even represented in climate models. And this is based on also my read of previous IPCC reports, where SOA itself was thought to be so uncertain that, either it was not included, or if it was included, it was included with a very simplified way. So all these detailed chemistry is not present in our system models, and it's not even present in many of the regional models we know of. The IPOX SOA and also, right, this size variation of this chemistry is not included, because many of the models just use a modal approach with a few size, or even if they use a sectional approach, it's a small number of size bins. So the short answer to that is many of this chemistry is not even included right now in models. We, based on box models, or for example, if we are running a master chemical mechanism, we could run it in a box model sense, and then start to understand the processes which might be more important. But without including them in larger scale models, we don't know the full extent of this, of the implications of these processes. And that gets back to my point that if we don't even include these processes, we don't even know what we don't know. And this, for this IPOX SOA example, we also found that so for example, our system models were not including the phase state of these particles, their transition from liquid to solid phase. So if that was not included, and you run an IPOX SOA module, you would predict that you would make a lot of IPOX SOA in the upper troposphere too, because the particles are treated as liquid-like, which is not true. right? So you would not discover that there is gaps in our current understanding. Once we include the solid phase state of particles, we know that aqueous chemistry cannot happen. And then there are other processes like cloud convective transport of semi-volatile organics and their condensation, which I discovered during one of my previous work on which this work was built. So by treating these processes correctly in the model, I was first able to identify a big gap in current modeling approaches and then go after that gap and figure out what processes could explain the gap to get the right answers for the right reasons. So many times there are compensating errors in the models and uncertainties which we don't even know of.
Okay, I got it. Thank you so much. I appreciate it.
You're welcome.
Okay, do we have any additional questions? Please raise.
I have
Yeah,
a
go
last
ahead.
question, Horst. Just back to the DNN selection and training approach, how do we ensure that there's stability in the predictions across the timescales that you mentioned, especially given that you're looking at 20-to-1 ratio between the test time and the training timescales of about 7 hours versus 21 days for the testing? And maybe a follow-on to that is, did you consider looking at LSTM, for example, rather than just DNNs?
Yeah, so maybe I can answer your second question first. Because we are embedding this model into WRF-Chem, the time series predictions come from the WRF-Chem model because we are only replacing a module within the WRF-Chem model. We are emulating the aqueous chemistry model. So we did not have to do LSTMs in our case because our objective is to just represent the relations between input variables of chemistry and metrology and IPOX SOA formation within that aqueous chemistry module, and everything else, the time series predictions are coming by the default WRF-Chem model. So that was the reason for choosing a DNN emulator in our case. And then coming back to your first question about stability, so we were running, like we were taking 5-minute outputs. And so with very high time resolution outputs, we were able to see that the errors were not actually building up in the whole 3D spatial domain with respect to time. So the root mean square error, which I presented before here, these root mean square are over the whole 3D domain of every grid point in the model when we are comparing the default WRF-Chem model with the DNN embedded in WRF-Chem. And we see that as we see the progression, like this is day 1, day 2, day 3, the root mean square error is not building up as it would be building up over just hourly time scales, as I showed here before, that normally models have struggled with quick building of these errors over several hours. But here, like if over the whole 3D domain, if we are not seeing this buildup of error accumulation, this gave us confidence that the model was stable. But I would like to invite Himanshu Sharma, who is a co-author on this study, to see if he wants to add anything to this question. Himanshu?
Yeah, hi. So in response to the question, I would like to add that with respect to the stability issues, we did not experience any instability for now because the embedding is not directly predicting the concentration, but the fluxes. So inherently, the model is trying to predict the change and add that change in the module that WRF-Chem is using. So in predicting the fluxes, we were inherently capturing the notion of any instabilities that the simulation might go into because of the wrong predictions. So we were, I would say, implicitly handling that. And then with respect to the LSTM model, I think Manish already addressed that question. So LSTM models were possible, but again, we were tied to some of the limitations of WRF-Chem itself, that embedding complex models for the very first attempt would have been a really challenging process.
Thank you. Very clear. Just a very quick follow-on to that, since you mentioned you used fluxes versus concentrations. So have you quantified actually mass conservation performance then, if you're only considering fluxes and not concentrations?
So because we are predicting the fluxes and we apply the fluxes outside the DNN emulator. So if we have an aqueous chemistry module within WorkChem, we train the emulator to predict, given this input of meteorology and chemistry variables, if hypox SOA is taken up by the particles, this would be its flux out from the gas phase and flux into the particle phase. But we do not apply the fluxes to concentrations within the emulator. We apply that outside the aqueous chemistry module. And so in that sense, the flux which we take out from the gas phase is exactly applied to the particle phase. And in this way, we exactly apply mass balance. Because the emulator is not applying that mass balance. We are just using the emulator to emulate fluxes, and we apply the mass balance outside the emulator.
Understood.
At each
Thank
grid
you.
cell with time as the model is running, at every grid cell at every time.
Well, I think we've reached the hour, and unless I see another hand or somebody else speaking up, then I think we should conclude the session here. I'd like to thank again the speaker and the co-authors for their presentation, for being with us this evening, and I would like to thank all our reviewers for your support of that long review process, and I hope I'll see you all, or virtually at least, next week, Wednesday, for our third presentation. Have a good night or good morning or good afternoon, wherever you are. Bye-bye.
Thank you. Thank you, Manish.
Thank you, everybody. Goodbye.
Thank you.
Thank
Bye.
you.